Okay, so it's week 11, and we're going to do fuel cells. So let's get into the lecture here. Okay, so I'm just going to move through the fuel cells. Fuel cells week. So here's the weekly reading assignment. So get into your textbook. You're going to read chapter 11. And there it is. Here are the chapter notes. And I'm just going to dive into this a little bit. Okay, so there's our Carnot efficiency right there. Pretty familiar with that by now. We've done all that in 101. So the question is, why aren't we halfway down the road to the hydrogen economy? And just today, for what it's worth, we were back there in the lot working on our Chevy Silverado, which is not a fuel cell, it's actually a hydrogen combustion. Okay. So storage is an issue. The hydrogen tanks that we have here at the university are 5,000 psi, or double what you'd see in a conventional tank. But once you get to the fuel cell level, all the pressure is just at ambient pressure, or slightly above atmospheric pressure. We have definitely covered this in class, and just to reiterate on what these equations mean as you're going through, we know that power equals energy divided by time, and the way to visualize that is as time moves in this direction, we can think of the amount of energy being spent here, and then power is just a measure of how quickly energy is being spent. So when we look at that, we can have a little change in energy right here, and we can have a little change in time right here. So power, of course, is just the slope of that line. So another way of writing this is power equals delta E delta T, because obviously the power that's coming through an engine, it's going to be greater when you're accelerating or going up a hill, and less so when you're going down a hill or going on the flat. But then if we want to look at one exact power at this point, the way to write that would be power equals dE, and you can just think of D as being a smaller delta, and then dt, or another way of writing that is just power equals E dot. Well, the dot just means the change in time at a particular instance. So that's the calculus lesson for the day. Friction and drag swap places at higher speeds. As we remember from our wind turbine courses, that power is a function of the third power of velocity. And then the way to write that would just simply be that power is proportional to velocity cubed. .65 kilowatts, we can convert that to horsepower. Let's just do that. So 65 kilowatts equals 6,500 watts equals, and then if we just run that through, 6,500 divided by 746 equals 8 horsepower. So not too powerful, but not too bad either. William Robert Grove built the first fuel cell, gosh, almost 200 years ago. You can run at low temperature, so we're not constrained by the Carnot efficiencies we looked at a little bit ago. Methanol, also with its high hydrogen content, could be a fuel for a fuel cell. This is the fuel cell attains its best efficiency when partially loaded, and that's you can think of that in terms of running a bicycle or any car. If you're simply spinning your wheels or spinning around, your efficiency is very low. So as long as you have some pushback, your efficiency is going to be greater. That's what that means. Fuel cells have a very high energy density, but lack the power. It's difficult with all of the complicated electrochemistry flowing through a fuel cell to get the large mass flow rate of the fuel through to combine with the oxygen and then make your electricity. So there you go. You need a catalyst to assist the hydrogen atom to release its electron. And then the proton flows through, and that's where the electricity comes from. So that's the difficult part. And then oxidation is obviously an issue as well. And there have been a few false starts with a $3.8 million facility. And I think, it's a lot of it's still in the R&D phases. Okay, so here's a neat little diagram on how it works. So here comes your hydrogen, and the hydrogen atom is as simple as possible. It's just a proton, which you can see here. The protons are sort of heading up through the proton exchange membranes. The electrons are coming down through the circuit. It's a little light bulb light. In this case, the light bulb would actually be a motor, an electric motor. And then as this comes through, the combustion of hydrogen, here they come, and here come the oxygens, come through, and then there's your exhaust. So hydrogen supply, air supply or the oxygen, water management coming out, and then heat. So both sides are pressurized. You need some compression to get through there. Okay, so here's the overall efficiency, and this is how easy it is to use the hydrogen coming through, what the stack efficiency is, then any parasitic loads, and that's just the valves and pistons and whatnot as they create friction. And the stack is just whatever heat is lost going through the main membrane components. One example, Chevy S10. And they've run these with as hybrids so that the battery can also be used to upgrade the efficiency. Our Chevy truck does compressed hydrogen, and our Zeus does solid hydride. So the hydrogen is not in a gas form; it's actually absorbed onto a membrane. Absorption means it's inside. Adsorption means it's on the outside. Here's some of the problems. We don't have the infrastructure yet. Distribution. Hydrogen fuel cell, $61 a kilowatt. $61 a kilowatt. Let's just do that really quick. $61 per kilowatt. So that's 6100 cents per kilowatt is 61 cents per watt. Now, that's actually kind of cheap if you look at it from a solar cell. So, why that's a hurdle, I don't know. It actually seems pretty good. $61 a kilowatt. The Clarity, which is some of the early Honda vehicles, cost $500,000 to make, and that's well outside the price range. Relatively short range, and they have to be warm. That membrane needs to be warm in order to work. So to be competitive, you need to get down to $10 to $15 per kilowatt. So supercapacitors for energy storage, battery, here's your fuel cell. Everything's DC until you get to your motor. So there's your inverter to get up to your electric motor to the transmission. First fuel cell vehicle. God, it's gorgeous, isn't it? So the fuel cell market is actually fairly well developed. Here's where it starts to get interesting when you add value from CO2 emissions and health benefits. So lack of the junk pumped into the air. Platinum catalyst to pull that hydrogen apart. Non-platinum catalyst, been ongoing for 40 years, maybe a little further along. Okay, well that's the reading. Great notes, by the way, Brian Kearns. Thank you very much. Very much. Okay. Week 11 discussion. I'm going to add a new one. I-5 and I-15. Do a little research and see what the latest buzz is on the hydrogen. Let's say the rehydrogen I-5 and I-15 corridors in California. Submit. Do my own research here, see if I can't find something. Nothing in the news, nothing in the news, nothing in the news. Oh, maybe this is it. Oh, let's check it out. Okay. Stations map. Fuel cell partnership. Find the nearest hydrogen stations. Well, let's just start out. And here's zip code 59802. Go. Uh-huh. Quite a ways, quite a ways. Lake Tahoe. Well, there they are, folks. I mean, they're, looks like they're for real. Let's go ahead and zoom in here. There they are, details. Let's take a look at the Harris Ranch. Online, station, retail, fuel pressure, website, visit. There it is. Let's look at the fuel pressure. So they're running 35 or 70 MPa. 35 MPa equals, let's see, let's just do that really quick. So 35 MPa equals 35,000 kPa. Right, so multiply that by 1,000. 35 MPa. So if we start with 35,000 kPa, we want to turn that into atmospheres. We know that one atmosphere is 100 kPa. There we go. 100,000 pascals, right, equals 100,000 pascals. Let me just erase that. Tools. Eraser. There we go. Tools. So, 100 kPa, 1 atm equals so 35,000 divided by 100 equals 350 atmospheres. And if we want to take that to PSI, 350 atmospheres one atmosphere is 15 psi, or maybe 14 psi. Let's call it 14 equals, so 350 times 14 equals 49,000 or 4,900 psi. And that's double what a typical tank is. So these are not your standard tanks. And you can also see that they'll also run at 70, which is twice that. So let's visit their website. Zero. Next Gen Electric Vehicles. There's some partners, State of California. Did not see. It's pretty good. 2 million zero emissions driving. September 16th, electric vehicle mileage record set in California. Let's check that out. That's cool. Look at that. 1,400 miles in a 24-hour period. Huh. Nice. That's cool. Foreman at Phillips. Retail hydro station. It's time to call these guys up. call these guys up right now. Give them a ring. Now let's even share it. Share it on Twitter. That's how we do it. Tweet. Tweet. There we go. Let's go. Let's see if we can contact movement partners. 0 BMW. Site by information. I think these are the guys that contacted me. Let's contact us. Let's see what's going on here, guys. Contact us, menu, FAQ, fill out how it works. FAQ news. Where's that come from? 2/3 renewables. Okay. Save. Okay. Why these guys don't have a better contact. We'll just do it through a station. Santa Barbara. Good directions. Let's try another one. What do they call these guys? What do they call themselves again? True Zero? True Zero contact. Yeah, we'll just have to get on the phone. Okay, that's all I got time for today. We'll just have to get on the phone. Let's see if we can't do one example problem. pressure conversion for you there. Okay, I5. So I did my own little research, but it looks like it's moving forward. I mean, that's really cool. It's really cool to see that happening. Let's do the example problem. Okay, as we've seen in the textbook drafts of results, we can often need to interpret data and find numerical values for conditions specifically given. That's our interpolation we've done already. Interpolation and extrapolation are two techniques. You can probably read that a little bit better now. There are ways to mathematically fit a curve or a line through the data. This process gives us a mathematical equation that we can use to find any value we desire. Fitting a curve is often a difficult process, except for the simplest curve forms. Simplest is a straight line. We're given 2 points. We can compute the parameter. Okay, that's cool. Nice. That was just kind of old hat. All right. We want to estimate the cost of a hydrogen storage tank that's rated at 15,000 psi. We know that a 3,000 is 1,700, and a 9,000 is 3,200. We can figure out the cost at 15,000 thusly. Nice. Nice. Well, if it's linear, then that's great. I'll take you through that graphically. I'll take you through that graphically. So we have PSI rating, and then we have cost over here. So if the PSI is 3,000 and the cost is 1,700 versus a PSI rating of 9,000 and the cost is 3,200, since it's pretty straightforward. 3,200, what we're looking for is the cost at 15,000. So just to wrap up here, what we're looking for is this number right here. So if we, let's just go ahead and plot this. So we're looking at price as a function of PSI. And so the two data points we have are 3,000, or we have 1,700 and 3,200. 1,700, and we've got 3,200 here. And PSI is 3,000 and 9,000. And 9,000. So here are our 2 points, and what we're looking for is for 15,000, which I'll just put way out here. 15,000. What's the and so visually we can see that it's right about yay, but now we want to get that number. So the way I would tackle this thing, if we had this as let's just go ahead and call this X, and we'll call this Y. And so we know that so this is going to be X1, Y1, this is going to be X2, Y2, and this is going to be X3, Y3. And so we know that Y y2 minus y1 over x2 minus x1 equals y3 minus, now we can choose either one. We can choose the middle point or we can choose the leftmost point. Let's just choose the leftmost just for grins. No big deal. You can do it either way. y3 minus y1 over x3 minus x1. So let's go back to our data. y2 is 3,200. I'll just drop the zeros. So 32 minus 17 over 9 minus 3, and just drop all those zeros. Now it's going to come out the same. Equals y3, and we'll just call that y3 minus y1, which was 17 over x3. We know x3 now is at 15,000. 15 minus 3. So if we see if we can't get that onto a new page. So 32 minus 17, that's what, 15 over 6 equals y minus 17 over 15 minus 3 is 12. So if we just run that, so from here we'll multiply both sides by 12, so just times 12. So if we throw a 12 right here, 12 divided by 6 is 2, that becomes 30, equals y minus 17. Y equals 30 plus 17 is 47. And if we go back, we know that's going to be $4,700. There's your answer. Okay. There you go. So there's just linear extrapolation. So no real guarantee that this thing is going to be linear, but it's a first order approximation on pricing out tanks. More than likely, I'm thinking as your PSI goes up, you're going to have something that's going to be more parabolic. But anyway, good problem to do. So, hey, good luck with the homework. Good luck with the quiz, and we'll see you soon. Also, let me dive right back into the course on one last thing. Yeah. So please do submit this term paper. And here again, here are the guidelines. I think you've done your visits, and we've gone over this before, so that's what you're looking at for your term paper. All right, thanks everybody. See you next week.